Thank you very much. Okay, I would like to introduce myself. I'm not very far from the previous speaker. I'm also from Israel, from Holon Institute of Technology. My name is Laikhtman from Physics Department, and this work was performed in collaboration with the tribology group of Levin Rapoport and from the group, chemistry group from Bar-Ilan University of Tzuri Levin and Jean-Paul Lellouche. I'm also a specialist in spectroscopy and microscopy. They are real tribologists and mechanical scientists, but I would like to present this, our collaborative work. So my work is related to nanostructures of tungsten disulfide, anorganic nanotubes, but I would like first to give you some ideas why these nanoparticles are such popular in different applications, because they have lead structure, semiconducting properties, not the best, very high thermal stability. You can see here the data: chemical stability, input resistance, high modulus, dispersion, good adhesion to polymers, which is related to this work. The most important, that they can be synthesized in commercial quantities, so you can just buy them, though we produce them in our laboratories. They have improved lubrication properties also with surfactants, building blocks for new electronic and chemical sensing devices, and also we can dope them with different compounds, different elements to even further enhance their properties. And also I will talk very briefly about this issue. So just the preparation, the synthesis process for example, for fullerene-like nanoparticle, this is a multi-step process, which always starts with the oxide in hydrogen atmosphere. We produce the reduction from outside to inside, and in such a way we produce layer by layer this nanostructure. It's more onion-like, but for traditional reasons, for historical reasons, it's called fullerene-like structure, and it was discovered and synthesized first by Reshetnev in Weizmann Institution in 1992, but the commercial synthesis was available from 2009 by the company and then by the group of Al-Azhar, who is now also my colleague in HIT. And these structures are very, very different from amorphous, well-known MOS2 or WS2 that you can buy commercially, that are additives to fuels and so on. So these are very different structures. In this work, I will all concentrate on anorganic nanotubes of the same material. So chemically it's similar, but technically it's a very different process. Again, we start from oxide, then mild reduction by hydrogen. We reduce the stoichiometry of hydrogen to tungsten. We produce the nano whisker of oxide, and then from outside to inside there is a sulfidization process, and finally we have this multi-wall nanotube with open ends and hollow core. Here you can see how the materials are looking like, fullerene-like structures and nanotubes. They range from 50 to 120 nanometers width and up to 20 microns long, but generally they have 5 to 10 microns long and with open ends. We can now produce also single-wall nanotubes, but they are still not very commercial, in commercial quantities, so most of the materials are multi-wall. In our previous work, we already improved the lubrication properties of these materials, mainly based on MOS2, but also in WS2 fullerene materials by their doping with rhenium. This resulted in a reduction of friction coefficient due to Coulomb repulsion. So there was a decrease in surface resistivity, and then because of this property, there was the lubrication increased very dramatically. But the problem with this one, that it was not very homogenic, so the reproducibility of the process was not the best. And as always, the problem was fullerene-like nanoparticle, that the durability of the surface is not the best, and also the size of fullerene particles is not homogeneous. It goes from 50 to 150 nanometers, and so the properties are also can be different from one batch to another. So here, going to the main part of my work, we started with anorganic nanotubes. INT means anorganic nanotube WS2. By themselves, they can be used by lubrication material, but not very good one because they are too big. So, and also the problem is their agglomeration. Here you can see the agglomerates of this pure INT. So we should add some surfactant. So we would like to use one which is Teflon, namely polytetrafluoroethylene, which is also good as self-lubricating material, but with different problems like thermal stability, for example, and it can be also easily washed by other chemistry materials and in hard conditions. So this is some preparation procedure. So we use two types of samples with different concentration of Teflon is related to WS2, 1.4 weight% and 5.6 weight%. So the procedure was quite complicated, but finally we got our materials that are covered with Teflon. How can we see that they are covered with Teflon? By TEM images. You can see although reduction in agglomeration of nanotubes. So I will see later in the next slide, I will see the quantitative analysis of the average size. But as we increase the concentration of Teflon, you can see that the tubes are more and more separated, and these nanospheres, giant nanospheres, are mainly the Teflon related to Teflon. And also in the case of high concentration of Teflon, we can see multi-layer coating instead of single layer as in lower concentration, but I will go to this point later. So here there is an average size distribution of nanotubes. These are pure nanotubes, and these are Teflon covered nanotubes. So the average size decreases from more than 2 microns to less than 1.5 micron. So we consider that Teflon prevents formation of aggregates by coating their surface. And the XPS analysis showed this in a more precise way. Because we have more and more carbon and fluorine close to the surface when we treat our nanotubes with Teflon. And thermal gravimetry analysis also showed that the weight loss is entirely from Teflon and not from nanotubes, because they are very stable up to about 1000 degrees, so even up to 500 degrees there is high thermal stability, and only after this there is decrease in the weight due to Teflon. So we don't compromise their stability. And now for the friction test. So these are standard friction tests with steel ball and plate. These are hardness values. These are contact pressure, velocity, and the number of cycles. The tests were performed in PaO4 oil, polyalpha-olefin oil. So these are friction coefficient for the oil itself, and also the size of the wear spots. And as soon as we introduce nanotubes, also already decrease in the both friction coefficient and wear spot. And for this type of relatively low Teflon concentration, we have the best conditions. So the friction coefficient is 0.12 and wear spot is 77. When we increase the concentration of Teflon, it was not clear to us before, then the friction coefficient slightly increases as also the size of the wear spot. So it followed that we have to use this intermediate concentration of Teflon for the best conditions. These are scanning electron microscopy images of wear tracks following the friction. So with the pure nanotubes, you can see these plugging tracks appeared on the surface of the plate, and these are undamaged nanotubes inside the tracks. But after friction with nanotubes covered with Teflon, we see that there is some fracture of nanotubes. So fracture is not always bad. And this fractured nanotube, they enter into the surface in the contact area, and in such a way they reduce the friction coefficient. And on the contrary, when we have too much Teflon, then there is limited supply of nanotubes to the interface, and again we have some increase in friction coefficient and rare spot size. Also, the elemental analysis by EDS show that there is increase in carbon inside the tracks. Most of the carbon, of course, not from Teflon, but from the oil, but the increase is entirely from Teflon, as we don't have any other source of carbon during the process. This is our final analysis of micro-Raman chemical structure. So WS2, they have very characteristic two peaks related to E2G and A1G, 356 and 419 inverse centimeters. This is Raman of Teflon. Here you can see these two small peaks. They are sure related to Teflon near the surface. Unfortunately, the surface sensitivity of Raman is not the best, and the thickness of Teflon layer is on the very limit of Raman sensitivity, so probably this is why we cannot see this major peak of Teflon. But what's more important, not that we see this Raman peak, but what we don't see. And we don't see any change in the relative intensity of these WS2 peaks, which means that there is no damage to nanotubes. There is no formation of oxides generally observed in this area. I mean tungsten oxide, which is a very frequent process in the case of friction and temperature treatment and damage and so on. So the EDS and micro-Raman, they indicate that Teflon promotes penetration of WS2 nanotubes into the interface, though we cannot see it directly, as fluorine cannot be absorbed by EDS, and Teflon layer is very thin, and this presence of PTFE structures in the contact interface facilitates shearing, and thus we suppose that it's responsible for the decrease in the friction coefficient and wear. So now I come to conclusions. Tungsten disulfide WS2 nanotube was successfully functionalized with Teflon using BAP sonification. Our analysis by TEM indicated much better distribution, less agglomeration of Teflon-covered WS2 as compared to nanotubes, and they were clearly absorbed around the nanotubes. So the addition to oil provided the best friction and wear properties, and this is because of fracturing of the nanotubes covered with Teflon, unlike pure nanotubes, which remain in their pure condition, and thus this fracture, or let's call it deterioration of nanotubes, facilitate their penetration to contact interface and are responsible for improvement of friction wear properties. We have some ideas for our next work. We'll try to do this for fullerene-like nanoparticles. Unfortunately, it's not that easy to cover them by Teflon. We have to invent some different procedure. And also another promising direction is to achieve control of the orientation of the lubricant, which can also which can also be beneficial for this project of both increase the durability and decrease the friction of this lubricant. Thank you very much.
Time for one quick question. Yes, please.
Thanks for your presentation. I have one question. As you mentioned, your materials WS2 is not a amorphous lattice structure. So are there any evidence to prove such as XRD and TM?
Sure. I didn't show this here, but there are numerous XRD measurements that we do. These are just standard. The material is not very new, so it's produced from 90s, and always for every batch we have XRD, and then of course it's this is not amorphous. Also, you can see this in the TEM here. These are nanotubes, and the amorphous looks very, very good.
Okay.
Okay, because if you do high resolution, then you clearly see the layers like here.
There's one more quick question back there. Yes, please.
We have used the materials as, I would say, additive to oil, right? So liquid lubricant.
Yeah.
Would it be interesting, or have you tried already, to add it to a polymer and to use it as a solid lubricant system?
It could be possible. I think the problem was with the testing. So I think that the test machine, the friction test machine, was it was possible to use only oil wet friction, but not the dry friction. So I think this was just a technical issue, but for sure it could be applied for solid rocket.
Maybe we can help you with that.
Yeah. Well,
Okay, thank you very much.